We saw in the previous video that the mass balance or balance of any conserved quantity can be written through a sum of net mass flow out of the volume due to concentrations in the flow plus the net generation of mass within the actual volume, this volume integral of source terms, which I've now put on the other side of the equation here with a negative sign in front. And that's equal to the net decrease of mass in the volume per unit time. So the negative sign means it's a decrease. So dm by dt is the net increase of mass in the volume per unit time, and then putting a negative sign out front means it's a net decrease in volume. And we use outflows as positive, as our positive sign convention, to be consistent with our use of the outward pointing normal as the positive direction. So in our previous video we were looking at a general volume, but to understand what happens to this surface integral as we shrink our volume of interest down to an infinitesimal point, let's look at a sort of slightly less general volume, but the logic here will apply to a general volume as well. So we have this rectangular prism, which is dx by dy by dz. It makes up a volume dv equal to dx, dy, dz. So the area on this side right here, ds, is actually dx times dz, the area of this face. And then on this face over here, the area is dy times dz. So to understand how this works, this surface integral works, now we have a sort of very regular volume where we can assess the positive directions of this n vector conveniently because the faces are oriented to be perpendicular and parallel to the principal coordinate directions. So let's look at flow in the x direction. Flowing in at some point over here, we have an amount rho vx, where this is the x component of the flow velocity, and again rho is the concentration at a point, and then the area of this face of the unit volume is dy times dz. Flowing out on the other side is, so now thinking back to our definition of the total differential, we'll write the amount flowing out over here as rho vx. So whatever it was here over at x equals 0 plus d by dx of rho vx multiplied by the distance that we moved, dx. So to go from over here to here, we moved a distance of dx. So the magnitude of the flow over here, the mass flow rate, is rho vx at x equals 0 plus the change per unit change in x times the distance that we moved, dx. And then this whole expression here is again multiplied by the area of the face. So dy dz. Okay, so now looking at this expression here, we can directly sum mass rates flowing out minus mass rates flowing in the x direction. So in the x direction, sum of mass flow out minus sum of mass flow in. So we have rho vx plus d by dx have this quantity, rho Vx, multiplied by the distance that we moved. And then that whole thing is multiplied by the area, ds, which is equal to dy dz on this face, minus the flow rate in on this face. So we have rho Vx, again multiplied by ds, the area of that face, so dy dz. And this amount, if we cancel out terms here, we can see that this rho Vx cancels with this rho Vx. So actually we're just left with d by dx of rho Vx. And since this is the only term left, what we're left with is dx times dy times dz, which was our dv. So if that was the amount in the x direction only, we can arrive at a similar expression in the other two directions. So in the y direction, we'll have the component of this sum here will be d by dy of rho vy dv, and in the z direction we're going to have d by dz of rho vz times dv. So actually these three terms together make up the entire net balance of flow through this infinitesimal volume. So if we add all three of those up, we can actually see that we're going to erase this part here to write out the whole sum. So the sum of mass flow out minus sum of mass flow in for this volume is actually the sum of these three integrated over the whole volume. So integral over the whole volume of d by dx we have d by dy, d by dz plus we got each of our components here, rho vx, rho vy, rho vz, integrated over the whole volume. So this expression here, which was from our previous video equal to the integral over the surface of rho v dot n ds, is also equal to the integral over the volume of this expression right here. Which, if you think back to our video on the vector operator, actually this is equivalent to the integral over the volume of the divergence of rho v. Okay, so actually that will come to quite an important result from this set of logic, and we'll do that in our next video.